This video is about osmosis. So osmosis is the flow of small solvent molecules, which in our case, we really only refer to water as the solvent that does the flowing. The flow of small solvent molecules through a semi-permeable membrane from a region of low concentration of solute to a region of higher concentration of solutes. And a semi-permeable membrane only allows the flow of small particles. Um, so the first thing I'd like to do is show you, well, I'm just going to show you on paper how you make a shell-less egg. In other words, how you take the shell off of an egg, because as you know, there's a membrane under that shell that holds that egg in place. And I've done some osmosis experiments using these eggs without a shell, and I would like to show you the results because it does a nice job of illustrating the process of osmosis. Excuse me. So let's get started. So I've already said that osmosis is the flow of water through a semi-permeable, that just means it doesn't let everything through, just those small water molecules. So through a semi-permeable membrane from a region of low concentration of solutes to a region of high concentration of solutes. So the flow is really to equalize the concentrations on both sides of this membrane. Okay, so what is an egg, right? So here is a drawing of an egg, and as you probably know, right underneath that shell, there's a membrane, and sometimes this membrane really gets in the way if you're making hard-boiled eggs. I mean, if you're trying to take the shell off of hard-boiled eggs. And you know, of course, that there's the yolk, and then there is the white of the egg. Okay, but what I'm interested in is the shell. And the shell is made of calcium carbonate. And calcium carbonate reacts with vinegar. And you know that the ingredient in vinegar is acetic acid. And acetic acid is a CH3, C double bond O, OH. And this part we call OAC. And this is the acidic H, we'll learn later. So we call this HOAC. And this is really just an abbreviation. It's not the chemical formula. But when these two react, this is one of these gas-forming reactions of acids. So it's an acid plus carbonate. You may remember back from Chem 103. And we'll learn later that carbonate is actually a base. So calcium carbonate is actually a base, and this is an acid-base neutralization reaction. And so what happens is you end up with carbon dioxide and water and calcium acetate. And this is aqueous. So the basic thing is that you started out with this hard shell, and you end up with carbon dioxide and water and this other stuff. But basically, what you do when you put this egg in vinegar, because that's what we use. That I use vinegar, and I actually use 4 eggs, but I just put an egg in there, and very soon you see a lot of bubbles coming out. It's very frothy, and I basically left it there for quite a while, like 2 days. And sometime the second day, I started to, see if I could squeeze the egg, see if it still had some shell. I turned it a couple of times, I had to add more vinegar because it wasn't really getting rid of every last bit of the shell. And so I made these shellless eggs that I'm going to show you now. And then I'll come back and I'll talk about what happened. So these are the eggs that I put inside of the vinegar. And this one looks kind of whitish because I actually just scraped off the last of the calcium carbonate here with my fingernail on this one. And you could see that now it's kind of clear. So there's a little bit left of that calcium carbonate. See how I'm scraping it off right now. And then I can make it go away. But I didn't do that on the eggs that I used for my experiments. So they look more whitish like this. But they're both very squishy. And this is the membrane that's inside of the shell. So what I did was I took and placed an egg just like this into distilled water. And I wonder if you could see the difference here. That this one is actually, well, actually you can't tell at all, but this one on my right, this one here, is a lot larger than this one. I don't know why it's not coming out on the camera like that, but this one is actually the bigger one here. It looks smaller, but it's not. Anyway, forget about that. That was in distilled water. I'll talk about that, but what I really want to show you is the most obvious one. So look at this. This is a really disgusting looking egg, okay? Look how squishy it is. It looks like it's missing half of its liquid, or at least a good portion of its liquid. And what happened was, this stuff here, this ooey gooey, look at that yucky stuff, that's just Karo corn syrup, okay? It's really thick. It's a really strong concentration of sugar in there. And so what happened was the fluid in the egg actually moved out of the egg from because inside the egg, the solutes are at a lower concentration than outside the egg. And it doesn't matter that what's dissolved inside is protein and other things, and what's dissolved outside is sugar. It's the number of particles that matters. And so osmosis takes the liquid from lower concentration to higher concentration of solutes, and in doing so made this egg go from nice and robust and a little bouncy to being this sort of shriveled up thing. And that's all from osmosis. So I think I've said enough about that and gotten myself dirty. All right, so here are my shellless eggs. Let's pretend that that's just the membrane. I have a couple of them. And I took one of them and I put it in some distilled water. Okay. So now you've got this egg, and this egg has a higher concentration of solutes than distilled water. Just about everything does. So what happens is that the flow of water through this semi-permeable membrane will be into the egg, and so after a little while, your egg will be significantly expanded. I guess I should draw it a little bigger and exaggerate it. Okay. So you get an expanded egg. And now the sort of the opposite thing will happen. I took an egg, remember, and I put it in this Karo corn syrup. And what happened was the fluid flowed out because the Karo is more concentrated than the inside of the egg. So the water flows out through the membrane and it sort of shrivels the egg so that at the end it looks kind of like this, you know, the shriveled egg. Okay, so all right, so that's an illustration of it. let's talk about it a little bit more. So what happens is that in both cases, the flow is from low concentration to higher concentration. So the first question I guess I would ask is, if you have a container and you have a semi-permeable membrane, draw it like that, and this side, let's say you have a much higher concentration, okay, higher concentration of solutes and a lower concentration. So the question is the water only flowing in one direction? And the answer is no. The water is actually flowing in both directions. It's just that the flow of water from the low concentration to the higher concentration is much greater than the flow of water the other way. Okay? So the flow left to right is much greater than right to left. And, you have to ask yourself the question, why? Do water molecules have brains? Clearly they don't. So they don't know which way to move. Something has to make them move that way. Okay? So the answer is, why does this happen? And I guess I would say it's a probability thing. And that is, the more the water molecules hit the membrane, the more they'll go through the membrane. But what happens, and here's an illustration of it. So here I've got these big molecules. So these Mickey Mouse-like things, these are the water molecules. OHH, okay? And these guys are the solutes. And remember, the water molecules are pretty small compared to most solutes. So these might be, big sucrose molecule, or something like that. Even a chloride ion is pretty large compared to, its molar mass is much greater than that of water. Okay, so here's our semi-permeable membrane. And, these water molecules, they'll hit this membrane, with sort of random motion. But the fact is that these big solute molecules prevent the water molecules from hitting that membrane as often. So they kind of interfere. So so here we have the high concentration on the right, and here we have low or no concentration of solutes. And we have a net flow from left to right, and that's simply because the molecules, the solute molecules on the right, are interfering with the water molecules hitting the membrane. So solutes interfere with the right-left osmosis. So there is a net flow of water from the left to the right. Okay, it's just a greater probability that the water molecules will hit the membrane, and that's why osmosis happens. So you might say, well, okay, how could you stop this flow? And let's not forget that this is happening in a container of some kind, right? So what if you had this container and it had a movable wall here, like this wall could be moved, and you actually moved it to the left, to the left. So you squeeze down on these water molecules here, on this whole solution here, as you moved it in, you put a pressure on this side. So you apply a pressure from the concentrated side towards the less concentrated side. So now you're actually causing water molecules on this side to have a greater probability of going through the membrane than they did before. And so you had a net flow from left to right, but when you apply this pressure, what happens is that it equalizes, it basically stops the flow from left to right, because now it's promoting flow from right to left. So there ends up being no net flow in either direction after you apply this pressure. So the pressure that you need to apply to stop the flow is what we call the osmotic pressure. And we give it the symbol pi. Okay, that's why we call it osmotic pressure, because if you apply that pressure in the other direction, it will stop the flow. Well, there's other ways of looking at this, and here's a very good other way of looking at it. So let's say you have two containers like this. So you have, the container on this side, number 1 and number 2, and you can see here that 2 is much more heavily concentrated. It has solutes dissolved in the water. Actually, on the left, I'm just saying that this is pure water. So what's going to happen is that you're going to have a net flow in this direction of the water. It's going to try to dilute the solutes that are on this side. So as the water flows from left to right, what's going to happen is that this level here is going to go down, and this level of water is going to go up. And what you would notice at some point is that the liquid stops rising. So at some point, liquid stops rising on the right. Okay? I'm talking about this level here. Now, why is that? Well, this extra column of water here is exerting a pressure. It's exerting gravity. Basically, the pressure exerted from right to left is it's basically exerting a pressure that's equal to the difference in the heights, or it's related to the difference in the heights. So we have gravity pushes from right to left now. Okay, so we have the osmotic pressure pushing from left to right. That's the pi, that's the osmotic pressure. But then gravity is pushing the other way. Okay, and when these equalize, then the flow stops. So, so at precisely the point where the force exerted by this column of water going down equals the force from the osmotic pressure, when those two are equal, the flow stops, and the osmotic pressure is the pressure that gravity is pushing at that point. So it's very similar to this. When you apply this pressure this way, it could be applied due to gravity. That's kind of what I'm illustrating. But when that force from right to left equals the osmotic pressure from left to right, then it stops. So this height difference, if you converted it to pressure units, would be equal to the osmotic pressure. And we have a very nice formula for osmotic pressure, and it's going to look really incredibly familiar to you. Look at that. Pi V equals nRT. Gee, that sort of looks like the ideal gas law, except not really, because we're not talking about gases. No gases here. Okay, so what does this mean, right? This is the number of moles of dissolved solute. This is actually the gas constant, the same thing. It's the same number, which is really bizarre, but true. And this is the temperature. It has to be in kelvins. This is the volume of the solution. And this is the osmotic pressure. Now, what we normally do is we take the moles here and we divide it by the volume. So we have pi equals N over V RT. And N over V, right, that's the moles of solute per liter of solution. That is just the molarity. Okay? So we end up with the very closely related formula, pi equals M RT, but this M here, you have to realize it means molarity. Okay? And there's another complication. And the other complication is due to the fact that it is the number of particles that matters. So so it doesn't matter if it's a chloride particle or a sodium particle or a glucose molecule. This is what we see with colligative properties. It's the number of particles matters, not the identity. So that means that if you have an ionic compound, for example, if you have sodium chloride, and let's say you have 0.10 molar sodium chloride, well, that's actually 0.10 molar sodium ions and 0.10 molar chloride ions. If you add that up, that's 0.20 molar of ions. So we have to modify this formula. We say that pi is IMRT, where I is the number of ions. Well, I should say the number of particles per formula unit. So if you remember, NaCl is not a molecule, right? It's a formula unit. It's the smallest unit of a sodium chloride crystal. And so basically, when you dissolve NaCl, you get 2 particles for each, formula unit of NaCl. So I would be equal to 2. So you kind of have to double the molarity of the sodium chloride that you start with, right? You have to say, okay, well, it's really 0.1 molar sodium and 0.1 molar chloride. And we take care of it by using that I. So if I want to figure out what is the osmotic pressure exerted by a 0.10 molar solution of NaCl at 20 degrees C, which is 293 Kelvin. Okay, if I want to answer that question, I don't like the way this looks here. So this is the question. So we have to use pi equals IMRT. This I is 2. The molarity is 0.10 mole per liter. 0.08206 liter atmospheres per mole Kelvin times 293 Kelvin. And that comes out to 4.81 atmospheres, which is totally shocking to me because it's really a very large pressure. In fact, yeah, I don't even I can't even fathom it that a 10th molar solution of sodium chloride would exert such a high pressure. So let me show you why I think this is so amazing. So what if we had a setup like this? And I have a long tube open, not closed. And I have my semi-permeable membrane. And on the left, I have 0.10 molar NaCl. Oh, sorry, on the left I have distilled water. And on the right, I have 0.10 molar NaCl. Okay, and let's say we start with the same level. Okay, so time goes on, and what's going to happen is that there's going to be a net flow in this direction from the region of lower concentration of solutes to higher concentration. So we calculated that 4.81 atmospheres is the osmotic pressure. So let me convert that into something that we can think about with a little bit more familiar to us. First of all, if we were to convert this to millimeters of mercury, it would come out to 3.66 times 10 to the third millimeters of mercury. So 3660 torr. Okay? So that means that we would have to have a column of mercury that was 30, so that's 3660 millimeters, so that's 3.66 meters of mercury, high. Now, mercury has a really high density. 13.6 grams per milliliter is the density of mercury. If we were doing this with water, it is 13.6 times less dense. So that means you'd have to have a column that was 13.6 times higher. So let's figure this out. We have 3.66 meters of mercury, which is about 12 feet. Let's call it 12 feet. That's for the Hg. For water, we'd have to multiply this by 13.6. I'm not going to give you a problem like that, but this is the density of mercury relative to 1 gram per milliliter, which is the density for water. And if you multiply that together, it comes out to 160 feet approximately. So that means that this level of water would have to go up until there is a 160 feet difference in the heights. And that would exert enough pressure in this direction to stop the flow. I mean, to me, that is just, I'm just like blown away by that. That's just crazy. So osmotic pressure, it's really surprising, but it's a really big deal. And especially if we're talking about hospitals and intravenous fluids. Okay, so in the bloodstream, what you have is you got your fluids, the plasma, and then you've got these red blood cells that are in the bloodstream as well. Okay, let me draw the red blood cells a little bigger so I can illustrate what I'm trying to show you here. So here's your red blood cells. Now, when you give somebody IV fluids, what you have to do is you have to have the fluids, they need to have the same concentration of solutes as in the regular blood, the plasma. And the reason is because if you have, let's suppose you put too low a concentration of solutes in the IV fluids, and that goes into the bloodstream over here. We say that that is hypotonic. Okay, in other words, the concentration of solutes is too low. It's lower than in the red blood cells. Too low a concentration of solutes. So when you have a difference in concentration of solutes, you'll get a flow of water. So water will flow into the red blood cells. And guess what? They expand, and that is not good for your health. Okay? And that's what happens if you have a concentration of solutes that's too low. And then, of course, you can have the opposite situation where you have, here's your red blood cells and here's your plasma. And what if you put in IV fluids that are hypertonic? Hypertonic means there's too high a concentration of solutes. So then there's going to be a flow out of these red blood cells. It's going to look like my shriveled eggs. Okay? And then that's really bad for you as well. So when you do IV fluids, they must be what they call isotonic. With the concentration of solutes in both the plasma and the red blood cells, because I'm sure it's the same. Okay, and then there'll be no net flow of water either way. And I do have a picture to show you on what that looks like a little better. Yeah, so here is your hypotonic situation, where water will flow, as it's shown here, into the red blood cell. There'll be a greater flow in than out, and these will basically explode, these cells. Here's isotonic, where you have equal rates of flow. And then the situation where you have a hypertonic, we have IV fluid, so this would be hypertonic here. And then you'll have a net flow out of water out of the red blood cells, and then you'll get these shriveled cells, which are really very bad. Okay. There's just one more thing I'd like to go over with you about osmotic pressure, and that's to do a different kind of problem. You can actually use osmotic pressure to determine molar mass, and I'm going to go through an example of that with you. So a solution is prepared by dissolving hemoglobin, 35 grams, in enough water to make 1 liter. So we have the volume of the solution is 1 liter. We have 35 grams of hemoglobin. And then it says if the osmotic pressure of the solution is found to be 10 torr at 25 degrees C, calculate the molar mass of the hemoglobin. It seems like, how on earth can you calculate the molar mass? But it's not so difficult at all. The thing is, we can use the osmotic pressure, that pi, to calculate the molarity. Okay, and we know that molarity is moles of solute, moles of hemoglobin, per liter of solution. So then, if we take the molarity and multiply it by the liters of solution, that's going to give us our moles of hemoglobin. We also know the mass, that we use 35 grams of the hemoglobin. So if you take the grams over the moles, so you take the 35 grams and divide it by the number of moles that you get, that's actually the molar mass. So it starts with using the osmotic pressure to get the molarity. So let's do that. Okay, and remember, we have to take this 10 torr. If we're going to use the equation, pi equals mRT, this R is in liter atmospheres per mole Kelvin, so we have to get the pressure in atmospheres. But we know how to do that. 760 torr is 1 atmosphere. Okay. And that comes out to 1.315, too many sig figs, times 10 to the minus 2 atmospheres. So it's not a whole lot. Okay. So that's the pi. We got that. Oops, checked off the wrong thing here. R is a constant. T we know is 298. I think I said at 25 degrees C, I hope. Yeah, 25 degrees C, 298 Kelvin. So pi over RT equals M. And here's another thing. Hemoglobin is a protein. It's not an ionic compound, so you don't have to worry about the I. It's only when you have an ionic compound, really, or some other strange situation where you'd need to worry about that I. So we take 1.315 times 10 to the negative 2 atmospheres. We divide it by 0.08206 liter atmospheres per mole Kelvin, and the temperature of 298. And we get 5.38 times 10 to the negative 4th molar. Okay, now molarity is moles per liter. Okay, so molarity times liters is moles. By the way, we only used 1 liter, so the molarity is going to be exactly the same as the moles. Liters cancel, we get the same thing. And when we take our 35 grams of hemoglobin divided by the moles, we get this enormous mass. So that's pretty typical for a protein to have a mass. This is 65100, 65,000 grams per mole. Okay, all right. So that's basically the unit. That's the part of the unit on osmotic pressure.